thanks. First of all, thanks for the committee to give me the opportunity to present my work in progress. So this the core part of this, the construction is basically done, but it's still not really usable because of some, say bugs of Agda or some other, probably my implementation. But anyway, so after the talk, if you're interested and want to help me to finish, and just welcome. Thank you. Okay, so first, work in progress. And so first of all, in this talk, I introduce about Mtac. Mtac is basically a monadic tactical program language in Cork. And they have a paper present with the typing rules, operational semantics. I say, okay, with this I can do this in other languages. Try to do in a principled way. And the machinery I use is elaborator reflection. I think this is first proposed, implemented in Idris, and from the Rail still sold this to Agda, and also this elaborator reflection in Agda is not really well documented. So I think it's also a good experiment to try out what Agda's elaboration can do, and if there's any bug about this framework, and in fact there are lots of bugs. And that's one. So I will sketch briefly how to implement one of the constructs of Mtac in Agda. It's pretty simple, I guess. And in the end, I'll talk about some problems that need to be done, to be solved. So first of all, what is Mtac? So Mtac is basically the idea is to have to design the monads so that you can say something like, okay, the witness, the inhabitant of this tower is possibly some element, some value of some type A. So we construct the monad, we call it the circle, and circle A is basically can be understood as say it's possibly A. So it doesn't need to. It can be some exception with some variables that I couldn't find a proof. But if we have a value for possibly A, then we can kind of construct a composition of tactics, and which takes some A to another circle B, and you cannot compose this with another function which starts from different types. So that's where types helps us to guarantee that the composition of tactics is meaningful. And in this language, we also have meta-level pattern matching, so you can do pattern matching against expressions. So it's not just the constructors for your data types, because you can do everything you want. And they also have binders, abstraction, and name situation. So name situation also is called local names, local name declaration, something. So you can say I want to have a name for arbitrary type, and used just in the later in the inner context, so on. And this language also can generate meta variable. You can check whether this one is a meta variable. And you also have exception handling construct, and you can also do a recursive tactic. And I use different color because we don't really need this one in Agda, because in Agda I can just do recursive meta programs. And there are also some other constructs that are less interesting. So something like the print error information. So this is not very important. Well, it's important for debugging, but it's not essential, not the core of the calculus. And so here is the screenshots of my implementation. So you can see that the language itself is, I think, is quite instructive. So for example, you can see, can I see my mouse? No, I couldn't see anything, okay. So you can, if you read the first line, you can see that if the target to try to prove is the prototype, then what you do is just find the proof for the both types P and Q and return this and construct a pair. And here I use this Indian bracket notation. So it looks like I could do no pointer anyway. Yeah. So. So for example, and for the second one, if that's a counterpart, and so it kind of, and also extend the Indian brackets notation a bit. It's from the Conor McBride's she extension. So you also have a bar to indicate that alternative functors. So you can try the left-hand side part, say P first. If it fails, then try the right-hand side part. So the tactic itself is also readable, I hope. And about the Mtac itself, there's also operational semantics, and the most complicated one is probably this. And this says that if we have a list of patterns, and I'll explain this later. But that's the most difficult one, and I'm going to show how to do this. And rest of the parts of rest of Mtac is kind of also straightforward if you're familiar with typing rules of lambda calculus. So yeah. Okay. So first, let's see. What is elaborator reflection? So in one word, it's really reflection plus elaboration machinery. So you can access the type checking machinery during executing the macros or the meta programs. So you can check the type, you can do unification, you can issue the meta variable and so on. And it's first implemented in Idris, then in Agda, and I think the Agda's reflection framework is not really well documented yet, but it's still readable. So if you can try it and you find some interesting you can do, and there are some use cases that propose. So for example, you can use reflection to write tactics, proof automation, and you can also use reflection to combine your termination proof and to transform a journal recursion to a structural recursion, which the type checker can see that's actually terminating. And then the third one is about also a typical application. You can use reflection to write type class derivation and interactive code generation. And so in this talk, I'll give you one more use case. We can actually embed type-detected language using reflection and also get all the benefits about this typing information. Okay, so it's a bit surprising that it hasn't been done yet, considering that in 2016 when Christensen and Brandy, he talked about the possible application of elaborator reflection. Say, implementing Mtac's primitives would be an interesting use of the reflected elaborator. I say, it must be done. It must have been done somewhere, but we couldn't find it. That's very odd. Okay, given the culture of academic culture. So there are possible reasons that I can find in the literature. So in the paper on the Mtac, they criticize that text to be written using a debris index encoding all objects, blah, blah, blah. In Agda, this can be annoying, but not fatal. Okay, and the next one, so last year they have the Mtac 2 and also have the criticize. So the major limitation of deep embedding approaches is that the meta progress and tactics cannot be given meaningful time to describe their behavior in a way that Mtac 2 text can. That's kind of true because when you play with the reflection, all you get is just a plain data type about the reflective syntax. You get just a turn, and you have a deeper index. That's true, and so if you just do it directly, you have to play with the index shifting and weakening and strengthen. And we have seen a talk about this the binding issue. That's really annoying. That's true. And there's no meaningful types. Okay, I agree. If you just do it without any abstraction. So, but during my implementation, I found that actually there's only one construct that really need to manipulate the debris index, and the rest of them you can kind of use the reflection, elaborator reflection to get the effect, get the operation you want in an abstract level. And of course, and that's the whole purpose of the talk, is that using this elaborator reflection, we can also get the typing information available to the users, and when we developed the tactic, and so we still get the typing information. So, well, yeah. Okay, so so here is the kind of detailed parts about Agda. So Agda, we have data type for reflective syntax, because we have a data called term, and also another type, well, just equivalent to term itself is type. Well, it's different types of type and terms, they are no different, so it's reasonable to expect that they are of the same type. Some data types for meta variables, identifiers. So with the reflection in Agda, you can actually access the meta variables and check if that has been instantiated, been solved or not, and you can get information about certain identifiers, whether this is a type, or whether this is a function, and so on. And here's something that's really kind of getting interesting, is the reflection. Everything is done in monads, called type tracking monads. The type tracking monad captures the state about the current context and the context for meta variables, and of course also including the modules you have and so on. This is the monad kind of captures everything, kind of noises that you don't really care about when you do function program, that which has been handled by the type tracker itself. Okay, and then typically you also have a quotation on a quotation. So it gets if you have abstract value, you can get gets reflective syntax, and vice versa. So these slides are basically just the boring old reflection, but here's something interesting. We can do unification and textual terms, and we try to see if these two are unifiable. If that's unifiable, we can, So there might be some meta variables inside the terms. And so when doing the unification, you can also solve these meta variables. So that's why it's inside here, this type tracking monads, and returns nothing because the term is still there, but the meta variables might be changed. So, and also you can do type inference, you can do type tracking, and this also has some they also have side effects. For example, if you check some unknown term against some or any type, then you will get just a meta variable for that type. So it's not static. The type tracking actually changes something. And you can do reduction. You can do reduction to wicked number form, and you can also manipulate the context. You can get the current context and the extend, and in this one actually hits a bug of Agda, because when they extend the context, they forget to weaken the current variables, and so that's a bit strange. But yeah, there are some bugs, and try to fix that already. And you can throw some custom error messages if you want. So that's the base construct I actually used when I implement the Mtac. So not much, just 9 function. Well, not 9, but 9 categories of functions. Right. So next one, I'm going to say about how I actually define the circle, the monad. So the idea, if you look at it's pretty much, but the intuition is that the circle A is really just they apply this type tracking monad to the data type terms. So the values of circle A somehow present certain term, if there's any. And TC can contain some type check errors. Okay, so in detail, so the first case, the circle A can be just a reflected expression of that type A, or maybe a failure, so that you cannot find a proof, then you can return something, say, okay, this detective fails. And the next one, if you have other errors, say if you expose the local name to the outer words, then the language should also capture this error dynamically. Say, okay, this name is not try to escape its local context. So there are some exceptions that could happen during the execution, and the units and the binds are really just quotations and on quotation. So returns, so take A, then we take, well, just take its syntax, reflective syntax, and make it to the first case. And on quotation, basically, okay, if we have reflective syntax, then we take it on quotation of that syntax, then apply the function f to it, so then we get another tactic. So that's bind. That's intuitive. And also want to try to prove actually that is monads. Okay, so how to prove it is first of all assume that the TC is actually a monad. I'm not so sure. And the second one is, so if we, the quotation of two terms are equivalent or equal, then these two values should be equal. Be careful. And if a quotation followed by an unquotation, then that should just be returned. So quotation on quotation should not change anything. You should just get what you have in the beginning. And the fourth one that assume that is if they cannot be, so for any type A routes. So now we have to assume that we are talking about certain terms for type. And so for every, if these two terms cannot be distinguished by unquotation, then these two should be equal. That's a bit fishy, but by assuming this 4, then you can actually prove that this circular one is a monad. The first one is a bit weird because somehow you know, okay, there are different type errors, different kinds of type errors, and if you cannot unquote to this, if the unquotations are different, then it might be something, there might be different type errors, right? But here I can try to take the quotient and try to just identify all the type errors. But there are some big problems. Is that what does that mean between equality between expressions, and the kind of the correct notion between expression should be equality up to alpha conversions. And so if you have two terms which are alpha equivalents, then the quotation should be equal. And but it's not true if that they are just beta convertible, because 1 plus 1 is beta reducible to 2, but they are obviously two different expressions. And but the Agda does not have the equality for this TC monads, so it's kind of so the proof here is kind of informal. It's not really a formal proof. Okay, so I go through this pattern matching expression quickly. So first of all, we need the data type to encode the patterns and also the right-hand side of the evaluation. And so first of all, there's other things here is set omega. So because we want to also return the universe polymorphism, and so in this, and also cannot fix the universe label beforehand. So here we have to say, okay, so we just take this sort of set omega, which it can contain every universe, and also have this inconsistent feature in Agda. You say set omega in set omega. So this part is inconsistent, but this because it is only used internally, so you won't lead any problem. Okay, so first of all, so the first case, P base is just the patterns to be matched, P times Q, and if that's matched, then you can compute the right-hand side. So that's the first case, first constructor. And for the second one, so the second constructors are basically used to introduce the variables into the context. So you can see that you have a function C pattern P, and the P here is the variable name, and the underscore there is just the type which I ignored. One more minute. And so, okay, so the idea is try to replace every argument by a meta variable. And so we take, okay, I go quickly. So first of all, we just take the quotation of the type and generate a meta variable for that type and uncross that meta variable. So actually get the abstract value and apply that value to the function. Then we continue and until we actually reach the base case. And we will have the left-hand side, right-hand side, both argument position are replaced by meta variables. And we can do unification, try to see if they are unifiable. If that is the case, then we can return the right-hand side. Okay, otherwise there's type error returns. And other three and we build as first of all can pattern match do for one pattern and do many patterns, and that's just the pattern match for arbitrary expressions. So there's no deeper index we need to manipulate here. And so I implement 12 out of 13 constructs because the fixed points, the recursive tactics are not really needed in Agda. And there's only one construct which requires explicit deeper index manipulation. Most of constructs just cost about 10 lines of code. Okay, and there's no time, so there's on the GitHub, so you can try it yourself. And so there are some problems. So during the reviewer says, "Oh, can you do backwards reasoning?" Yes. So if you look at if we look at the implementation of Mtac 2, then the Mtac 2 is based on Mtac 1. So if you get Mtac 1, you kind of can get Mtac 2 with their implementation. But in Agda, because we don't have the typical ambiguity to accommodate different universes, so we only have one unique unified universe and so we have universe polymorphism, but we don't have the cumulative hierarchy. So in order to accommodate different levels of targets, we have I think we need a cumulative hierarchy of universe. And efficiency is really bad. If you tried, if we have a demo, then you can see that even a simple case may take a few seconds. And I guess partial regression might help. And the next one, what personally I will be more interested is what is elaborator refraction in theory and how we actually reason about these meta programs. And I guess contextual model type theory might help, or there might be some space for it. Yeah. So thank you.
So we have time for one question while our speakers switch out.
Yeah, so a beginner question, the level, universe level problems you were mentioning, the problem is you don't know the level of the proposition that the user is trying to prove using the automation. Is that correct?
Say again?
You mentioned several problems with universe levels.
The universe problem?
The levels.
Levels?
Yes. So the idea is that the levels that correspond to the level of the proposition that the user is trying to prove.
Because the subgoals of this might be in different levels. Maybe in different levels, you cannot really just fix one label and say, "Oh, I want to work with this one." And in order for the language to accommodate different labels of expression, and we need to kind of get this cumulative hierarchy.